Hello students. Now another spectroscopic method which is widely used in the study of biological molecules, not exactly into the structural aspects but in terms of their functional aspects, is the electron spin resonance spectroscopy. You have already got an idea about this. You might have heard the name when you are studying the membrane biochemistry. So, electron spin resonance spectroscopy is a very important method. Here again, resonance is being measured, and spin resonance, like nuclear magnetic resonance, here also spin resonance is being measured, and again it is electron, not nuclear resonance. Here it is electron resonance. Similar principle holds good here also. So, electrons being a tiny magnet, tiny positively charged moving particles, they are also going to act like a tiny magnet. So, they develop their own magnetic field, and this magnetic field, when external magnetic field is applied, it is going to show an alignment. And in electron we come across with again spin quantum number of plus of minus of, which are going to cancel each other, creates a diamagnetism. In a species where the odd number of electrons are going to be there, they are going to act like a paramagnetic, because the single electron which is going to be left over, based on its spin quantum number, it is going to have its own magnetic field, and this magnetic field orientation will be opposite to plus, means they are opposite for plus and minus. And when they are going to be kept under external magnetic field, they are going to have their own alignment and misalignment. And electron magnetic resonance is going to be seen whenever an absorption of microwave is going to take place. Here energy component, because it is electrons, so what happens is that they can absorb the electromagnetic radiation and the microwaves, and when they absorb the radiation of microwaves, they are going to show resonance at their magnetic field, and this resonance results, it's a result of the applied magnetic field, and the alignment is going to get altered. So, this alteration in the alignment, as we have known through NMR spectroscopy, we are going to measure, and that resonance is going to plays very important role, and that gives a lot of information about the particular atom or the molecule which is under study. So, all these formulas and all, we know that delta E is equal to H nu is equal to G dot B naught B naught. So, where B is a constant for Bohr magneton and G is a Landis splitting factor, and for a free electron in vacuum, so this factor is going to be 2.0023, and beta is the applied magnetic field, sorry, B naught is the applied magnetic field. Two possibilities exist for determining the absorption of electromagnetic energy. One is it can happen at constant frequency is applied, and we can vary the external magnetic field, and or we can keep the external magnetic field constant and vary the frequency. So, both kind of measurements are possible in ESR. In ESR, the basic principle wise, as I earlier mentioned, the odd number of electron, single electron will have its own magnetic field, and because of its internal magnetic field, so when an external magnetic field strength is applied of a proportional strength, there can be an alignment and misalignment is going to happen, and whenever an absorption takes place, and when we plot the graph, the area under the absorption peak is proportional to the number of unpaired electron spins. Most commonly, the first derivative of the absorption peak is the signal that is actually recorded. In case of a dienes like structures where delocalized electrons are going to be there, in case of free radicals and all, the G value is going to be the Landis splitting factor is 0.02023, but for localized electrons such as transitional metal atoms, this particular G value is going to be varied. See, we are going to, in case of electron spin resonance spectroscopy, we come across with hyperfine splitting of the peaks. Again, it happens because of interactions with adjacent nuclei. So here the electron magnetism is not just influenced by the adjacent electrons of the adjacent atoms, but also the nucleus of its atom itself. So there will be shielding and deshielding is going to take place. Okay, so this shielding effect is going to reduce the magnetic field, external magnetic field strength influence on the particular electrons magnetic field, and deshielding is going to increases the influence of the external magnetic field on the electronic magnetic field. This shielding and deshielding happens based on the nuclei which are going to be present around, and based on the electrons which are going to be present around of the adjacent atoms or adjacent molecules. So hyperfine splitting takes place by interactions with the adjacent nuclei. The number of peaks again which is going to be obtained is here depending upon the formula we can calculate, that is 2i plus 1, where I is the spin quantum number for the nucleus. With no coupling, coupling to one nucleus with the spin of plus half or minus half, we get two possible spins. When the resonance occurs, the absorption peak is going to be get broadened owing to the interactions with unpaired electrons. There is again, when you say relaxation, there is spin lattice relaxation and microwave radiation, and transfers from the spin system to its surrounding. Long relaxation time is going to be there, short relaxation time is there. Long decreases with the intensity of the signal, in the signal intensity happens. In short relaxation time, resonance is going to lines become wider. So in case of a typical ESR spectrophotometer, we come across with following parts within the instrumentation. One is radiation source, that is a klystron they are going to use, and sample chamber is going to be there, which is again between the poles of the magnet, and detection and the recording system will be there. The spectrum which is going to be obtained by the ESR is generally it's going to be of absorptive curve, or it can be of first derivative spectrum. This is how the instrumentation part is going to look like. Klystron, from there the microwave is going to be followed to that particular tiny the sample which is kept in a sample holder. Again the quartz sample holder which is going to be there, and sample is going to be usually liquid state, it is used here. And here whenever the there will be a crystal detector and attached to the computer. There is another side, there will be sweep supply which is going to be used if you want to change the, if you are going to change the magnetic field by using sweep supply, then we are going to use this, or if you are changing with the frequency, then we are going to use a change. We can alter the frequency in case of the by using a klystron oscillator. And instead of plotting the absorption that is versus magnetic field strength, it is first order derivative differential that is usually plotted against the magnetic field in ESR, and such kind of shape is called as EPR, electron paramagnetic resonance spectroscopy. People also call this ESR as electron paramagnetic resonance spectroscopy, also EPRs like NMR. So in case if the molecules are not having their own intrinsic resonance or intrinsic spinning, if it is not there, means odd number of electrons if they are not having, then sometimes people are going to use spin labels, so which can add up the extra electron into the molecule and gives the resonance to the molecule. So these are few of the spin labels which are people are using, just like we use fluorescent labels, probes, just in the same way these are the spin probes or spin labels. Application wise, ESR is widely used in a study of rate of catalysis, that is the studying the enzyme kinetics people are using this ESR. They are using in study of active site geometry of an enzyme, how exact what kind of molecules or groups or atoms are going to be there in the active site, and how they are involved in the catalysis of the reaction. People are using this method in protein folding, protein ligand interactions, structural changes in the DNA. They are using it in the study of membranes, how exactly receptor ligand interactions takes place in the membrane, how phospholipids interacts with the another phospholipid, or phospholipid is going to interact with the proteins within the membrane. All these are being studied by using ESR. There's a lot of things are going to be there with the ESR again. It's also one of the very versatile and very widely used method, but most of the studies which are done by ESR are pertaining to the functional aspects of the macromolecules, biological macromolecules or macromolecules, and even simple molecules, than that of structural aspects. Thank you.